Hi, my name is Nisa Bostancı, and I'll be presenting our work, DR-STRaNGe, End-to-End System Design for DRAM-based True Random Number Generators. I will first begin with a brief overview. Random numbers are important for many applications, including security applications, and DRAM-based true random number generators can provide true random numbers at low cost on a wide range of computing systems. However, no prior work on DRAM-based TRNGs provides an end-to-end system design to enable DRAM-based true random number generation in real systems. We identified three key challenges for using DRAM-based TRNGs in current systems. As DRAM is used as main memory, random number generation in DRAM creates an interference between regular memory requests and RNG requests, which we call the RNG interference. This can degrade overall system performance by slowing down concurrently running applications. This RNG interference can cause unfair prioritization of applications that intensively use random numbers, which are called RNG applications, and this can degrade system fairness. And due to the high latency of DRAM-based TRNGs, RNG applications can experience significant slowdowns. Our goal is to design an end-to-end system for DRAM-based TRNGs with low cost and high performance. To this end, we propose DR-STRaNGe, an end-to-end system design for DRAM-based TRNGs that reduces the RNG interference by separating RNG requests from regular requests in the memory controller, improves fairness across applications with an RNG-Aware memory request scheduler, and hides the large TRNG latencies using a random number buffering mechanism combined with a new DRAM idleness predictor. Based on our evaluations, we show that DR-STRaNGe improves the average performance of non-RNG and RNG applications by 17.9% and 25% respectively. It improves average system fairness by 32% when generating random numbers at a 5 gigabits per second throughput, and it reduces the average energy consumption by 21%. I'll start with a brief DRAM background. Here I show a system with a CPU and a DRAM module with several DRAM chips. Each DRAM chip consists of multiple DRAM banks, and these DRAM banks are accessed through one chip I/O. DRAM cells are organized as a two-dimensional array within each bank. A DRAM cell stores a single bit of information as electrical charge. To access a DRAM cell, its row is activated by fetching the data stored in the cell to the row buffer. A request is stored faster if the row is already in the row buffer. The memory request scheduler decides which request will be scheduled based on the current status of the DRAM. Commonly used memory request schedulers aim to maximize throughput by leveraging the row buffer locality. They prioritize requests to open rows over all other requests, then the older requests over the younger ones. Here I show a request scheduler with requests ordered in the age order from two different applications, and in the beginning, none of the targeted rows are in the row buffer. The scheduler first schedules the oldest request and brings row 1 to the row buffer. Other read requests to row 1 can be served quickly since the row is already open, therefore the scheduler schedules them next. Then, since there are no other requests to row 1, it schedules the oldest request, which is a read to row 3. Then continues to schedule in the same order. Let's continue with the motivation. True random numbers are used in many real-world applications, and the quality of the random number is especially important for a wide range of security applications, such as cryptographic key generation, authentication, and countermeasures against hardware attacks. Emerging security protocols such as quantum key distribution protocols provide stronger security guarantees against attacks that target weak random numbers, and these protocols require a very high true random number throughput in the order of several gigabits per second. Other use cases of true random numbers include randomized algorithms, scientific simulation, and statistical sampling. True random numbers are only generated by sampling random physical processes such as thermal noise, clock jitter, and Brownian motion. Systems can generate true random numbers with dedicated hardware true random number generators by sampling non-deterministic various physical phenomena. However, dedicated hardware TRNGs cannot be easily used in all systems, for example, embedded systems and processing in memory architectures. In contrast, DRAM is widely available in most computer systems and can be integrated into mobile and IoT devices as main memory. Therefore, high-throughput DRAM-based TRNGs have the main advantage of availability over other TRNGs that typically require dedicated hardware, and they can enable true random number generation within widely available DRAM chips. Next, we will look at the entropy sources within DRAM that can be used to generate random numbers. Previous research proposes a set of DRAM-based TRNGs that leverage the randomness in retention failures, which uses random errors in DRAM cells due to charge leakage in the cell's capacitor, startup values that form after power cycles, and timing failures that uses errors due to violating DRAM timing parameters. Retention failure and startup value-based TRNGs have limited throughput, since charge leakage is fundamentally slow and power cycles are expensive. However, random DRAM timing failures can be induced quickly using carefully engineered and time-valid sequences of DRAM commands on commodity DRAM devices. Therefore, they provide random numbers at high throughput with low latency, and they can be used in a streaming manner unlike other mechanisms. However, none of the prior work proposed an end-to-end system design to enable these mechanisms in real systems. We identified 3 key challenges for integrating DRAM-based TRNGs into a baseline RNG-oblivious real system: RNG interference, unfair prioritization, and high TRNG latency. Let's talk about the RNG interference. True random number generation in DRAM is time-consuming, and it can be very intrusive in a system that uses DRAM as main memory. Let's look at the memory request scheduling timelines of non-RNG and RNG applications when executed alone, and the timeline when they are executed concurrently on a system that uses DRAM-based TRNGs. This is the execution time of the non-RNG application, and when it runs concurrently with an RNG application, you can see each memory request gets delayed and the application's execution time increases. And for the RNG application, the interference increases its execution time as well. This shows the RNG interference incurs significant slowdowns both for RNG and non-RNG applications. Next is unfair prioritization of RNG applications. In a perfectly fair system, no application experiences slowdown when it runs concurrently with another application. However, in a system that generates random numbers in DRAM, memory request schedulers can prioritize RNG applications to achieve high throughput. And by doing so, the scheduler delays non-RNG applications' memory request more than the RNG request, and this creates unfairness. Here we show the memory request of 2 applications, one non-RNG and one RNG application. The scheduler can prioritize RNG applications for 2 main reasons. First, TRNG requires multiple DRAM accesses, so each random number request is translated into multiple memory requests. And second, RNG applications can have high required TRNG throughput and can create more memory requests. This results in RNG requests being scheduled more frequently to increase the overall throughput, and higher memory stall times for regular memory requests. This can increase the memory stall time of non-RNG applications and degrade system fairness. And the third challenge is the high TRNG latency. DRAM-based true random number generation has high latency and can degrade the performance of applications that intensively use random numbers. Here I show a code block from an RNG application, and it consists of 3 main parts. The first one is the part of the code that does not depend on a random value. Second is the part where the application requests a random number, and the third part is the code block that depends on the generated random number. Here is the memory request timeline of this application. After the unrelated code block, DRAM generates a random number to serve the application request, and this takes some time. Meanwhile, requests that depend on the random value are delayed. After the RNG is completed, DRAM serves the memory request from the code block that depends on the random value. As TRNG is time-consuming, RNG applications can suffer from long memory stall times due to the high TRNG latency. Our goal is to design an end-to-end system for DRAM-based TRNGs with low cost and high performance that minimizes the slowdown of both RNG and non-RNG applications, improves system fairness, and mitigates the performance degradation of RNG applications due to the high latency of DRAM-based TRNG mechanisms. Let's look into our mechanism, DR-STRaNGe. DR-STRaNGe consists of 3 main components tackling 3 key challenges. The first component is the random number buffering mechanism. It predicts and utilizes idle DRAM channels to generate random numbers, and stores the generated random numbers in a buffer to be served to upcoming random number requests. The random number buffering mechanism serves RNG requests with low latency. Second component is the RNG-Aware memory request scheduler. It accumulates RNG and regular memory requests in separate memory scheduler queues. It schedules the request based on the priority levels set by the OS. RNG-Aware scheduler reduces the RNG interference and improves system fairness. The third component is the application interface. It exposes the secure interface to applications that use random numbers, and this completes the end-to-end system design and ensures security. I'll explain how random number buffering mechanism works next. Random number buffering mechanism generates and stores random numbers before they are requested to be served in the future with low latency. It predicts DRAM idleness to generate random numbers with low overhead and stores them in a secure buffer. The key question is, when do we generate random numbers? We need to generate random numbers before they are requested to hide the high TRNG latency and reduce the RNG interference. We propose a mechanism that takes two key metrics into account to decide when to generate random numbers for the random number buffer. The first one is the low DRAM utilization metric. It shows if a channel is not fully utilized due to the low rate of memory accesses. And the second one is the DRAM idle period length. This shows whether the channel will be idle long enough to generate random numbers with no overhead. I'll explain the first metric next. We determine if a channel has low utilization based on the number of queued memory requests in the memory request scheduler. This gives us an estimate of how busy the channel will be in the next cycles. The random number buffering mechanism determines if a channel has low utilization by checking the number of requests in the queue and comparing it to a threshold called the low utilization threshold. After the channel is determined to have low utilization, we use the second metric to decide whether to generate random numbers or to wait. For the second metric, let's first talk about DRAM idleness. Applications often do not fully utilize the DRAM bandwidth, and this creates idle periods. Lengths of idle periods differ between applications based on the observed memory access pattern, and we can categorize idle periods into two classes based on their lengths. DRAM idle period length metric is used to determine if a channel will be idle long enough to generate random numbers without any overhead, and it helps the mechanism to avoid short idle periods. At runtime, it is not possible to know the exact number of cycles that the channel will be idle for. Therefore, we need to predict the future based on the observed memory access pattern. The key idea of our DRAM idleness predictor is to use the last access memory addresses to predict the length of the idle periods. We propose correlating memory access patterns with memory addresses that are followed by long idle periods. If a request to a certain memory address is frequently followed by a long idle period, this can point out to a certain memory access pattern, such as regular memory accesses leveraging the cache hierarchy. And then there's a good chance that in the future, the same address will be followed by a long idle period again. So our predictor recalls the address that precedes the long idle period and starts to generate random numbers after that address is accessed again. DRAM idleness predictor is a lightweight predictor that is based on a predictor table of 2-bit saturating counters. It uses the last access memory addresses to predict the idle period lengths. It also maintains a counter for the length of the current idle period. The prediction mechanism works as follows. First, if a channel is idle, it accesses the predictor counter with the last access memory address value. Second, the prediction is determined as short or long idle period based on the counter's state. And finally, we increment the idle period length counter as long as the channel stays idle. The update process is as follows. First, when a new memory request is received, the predictor gets the last access memory address value. It then checks the period length and compares it to a threshold that is called the period threshold and determines whether the past idle period was short or long. Third, it accesses the predictor table with the last access memory address and updates the counter value based on the evaluation of the idle period length. After the entry is updated, the last access memory address is updated with the new memory request address, and the idle period length is reset to 0. To sum up these two metrics and how to use them, our random number buffering mechanism works as follows. The mechanism first determines if a channel has low utilization by observing the memory request scheduler. Then, if a channel has low utilization, the mechanism gets the prediction from the idleness predictor. If the predictor predicts idle period to be long enough to generate random numbers, then the random number buffering mechanism starts to generate random numbers in DRAM. When enough bits are gathered, it stores the generated random bits in the random number buffer. This way, the mechanism generates random numbers only if DRAM is not fully utilized and the idle period is predicted to be a long idle period. Now I will describe DR-STRaNGe's second major mechanism, RNG-Aware Memory Request Scheduler. The RNG-Aware scheduler's goal is to schedule RNG requests without significantly stalling regular memory requests. There are two main issues with the prior RNG-oblivious scheduling mechanisms. First, RNG requests block regular memory requests due to the shared scheduler queue space. And second, the memory controller frequently switches between serving RNG and regular memory requests due to the RNG-oblivious scheduling decisions. We create our design based on two key ideas to solve these problems. The first idea is to accumulate RNG requests in a separate scheduler queue to reduce the contention for queue space between two types of requests. And the second idea is to use application priority levels to schedule RNG and regular memory requests with switching in between less frequently. Let's first talk about accumulating RNG requests in a separate scheduler queue. Without an RNG-Aware design, the requests are enqueued either to the write request queue or to the read request queue. Although RNG requests have different timing parameters, they perform read operations, and because of that, they are enqueued to the read request queue. This can cause regular memory requests to be blocked by the RNG request as they share the queue space. Our design creates a separate scheduler queue for RNG requests with the observation that they are essentially different types of requests. By creating a separate scheduler queue, RNG-Aware scheduler reduces the contention in the read request queue. This way, more regular memory requests can be enqueued to the read request queue. And the second idea of the RNG-Aware scheduler is to use application priority levels to schedule RNG and regular memory requests. The operating system manages shared hardware resources using application priority levels. RNG-Aware scheduler can use these priority levels set by the OS, and it can identify applications that use TRNGs by observing the differences between RNG and regular memory requests. After that, the RNG-Aware scheduler can prioritize different requests based on the priority levels. There are three possible cases regarding different priority levels. First, if an RNG application with an RNG request has higher priority than any other application, RNG-Aware scheduler prioritizes the RNG queue. This way, it can minimize the memory stall time of RNG applications. Second, if a non-RNG application with a request has higher priority than any other application, RNG-Aware scheduler prioritizes the regular read queue, and it minimizes non-RNG applications' memory stall time. And finally, if an RNG application with a request has the same priority as a non-RNG application with a request, then the RNG-Aware scheduler prioritizes the RNG queue to quickly serve the RNG request. This way, it can minimize the RNG interference and improve system performance. By employing these rules, RNG-Aware scheduler reduces the memory stall times of applications and improves system fairness. The third component of DR-STRaNGe is the application interface. Applications use existing getRandom system call, which is modified to support DRAM-based TRNGs, and communicate with DR-STRaNGe. If there are enough random bits in the random number buffer, DR-STRaNGe serves the request from the buffer with low latency. Otherwise, it will generate random numbers with low RNG interference and serve the request. I will share the key evaluation results next. We evaluate the performance, fairness, energy efficiency, and area overhead of DR-STRaNGe. We conduct cycle-level simulations using Remulator and DRAM power. We simulate a realistic system with the configurations given in the slide. For DR-STRaNGe, we use a 32-entry random read queue, an RNG-Aware scheduler, 256-entry predictor table per channel, and 16-entry random number buffer. We show DR-STRaNGe benefits using DRANGE and QuackTRNG as the RNG mechanism used in the system. For our single-core evaluations, we used 43 single-core applications from 4 different benchmark suites. We created synthetic RNG benchmarks with varying required TRNG throughputs. For multi-core workloads, we created 2, 4, 8, and 16-core workloads by randomly choosing multiple non-RNG applications and one RNG application. We compare DR-STRaNGe to two system designs. First, we evaluate an RNG-Oblivious baseline design, and second, a greedy idle design. The greedy idle design is based on the idea of a design with a perfect DRAM idleness predictor. If an idle period reaches the period threshold, we assume the design generates random bits without any overhead. However, it does not have a low utilization prediction mechanism. To simulate a fair comparison point, we also employ application priority-based RNG-Aware scheduling. To evaluate RNG-Aware memory request scheduler, we use two comparison points. First is the commonly employed memory request scheduler, FRFCFS with column cap of 16, and the second comparison point is a state-of-the-art application-aware memory request scheduler, BLIS, which uses the blacklisting method to improve fairness. We compare the dual-core performance of RNG-Oblivious baseline design, the greedy idle design, and DR-STRaNGe. We show the slowdown of non-RNG and RNG applications in workloads executed on a dual-core system, compared to the performance of each application when executed alone on a single core. DR-STRaNGe reduces the execution time of non-RNG applications by 17.9% and RNG applications by 25%. It also improves the average performance of RNG applications by 20%, compared to the performance of RNG applications when executed alone on a single core due to the lower TRNG latency. We conclude that DR-STRaNGe improves the performance of both non-RNG and RNG applications. It also outperforms both baseline designs by leveraging the idle and low utilization periods to generate random numbers. We evaluate DR-STRaNGe with 4, 8, and 16 cores and show similar results to the dual-core evaluation results. We conclude that DR-STRaNGe outperforms both RNG-oblivious and greedy idle designs significantly, and the performance improvement increases with the number of memory-intensive applications in the workload mix. We compare the system fairness of the RNG-oblivious baseline, the greedy idle design, and DR-STRaNGe. DR-STRaNGe improves system fairness by 32% compared to the RNG-oblivious design. We conclude that DR-STRaNGe outperforms both designs on average by employing an RNG-Aware scheduling policy and effectively reducing and controlling the RNG interference. To show the impact of the memory request scheduling, we compare FRF-CFS cap, Bliss, and the RNG-Aware scheduler. We show the performance results of non-RNG applications on top, RNG applications in the middle, and unfairness indices on the bottom subplot. We conclude that the RNG-Aware scheduler outperforms both scheduler designs, and it improves average system fairness by 16%. We evaluate the area overhead of DR-STRaNGe using cacti and show that DR-STRaNGe incurs minor area overhead compared to an Intel Cascade Lake CPU core. We also evaluate the energy consumption of the mechanism using DRAM power and show that DR-STRaNGe reduces the average energy consumption by 21%. Here is the list of other analyses and results in our paper. We discuss the security of DR-STRaNGe and show that the random numbers stored in the random number buffer are secure because they can only be accessed with a system call and the bits are discarded after they are read. We discuss the random number buffer as a timing side channel and conclude that DR-STRaNGe side channels are likely to be more difficult to exploit than timing side channels from other shared hardware structures. We discuss the random number buffer as a covered channel and conclude that countermeasures against covered channels such as partitioning can be applied to the random number buffer. We discuss denial of service attacks based on RNG requests and conclude that our RNG-Aware schedulers rules can prevent such attacks. And here is the list of results that you can find in our paper. We evaluate the impact of the DRAM Idleness predictor and compare the accuracy results of different predictor mechanisms. We evaluate a Q-learning-based reinforcement learning agent to predict the DRAM idleness by defining the DRAM idleness prediction problem as a reinforcement learning problem. We conclude that our lightweight predictor achieves similar accuracy and performance results to the RL-based predictor with less area overhead. Our RL-based predictor design is described in the paper. Please see the paper for more detail. We show the performance impact of the random number buffer with different sizes and conclude that a small buffer consisting of 16 entries can improve performance significantly. We evaluate the impact of the priority-based scheduling and low utilization prediction. We evaluate DR-STRaNGe with a DRAM-based TRNG mechanism with higher throughput, QAC TRNG, and show that DR-STRaNGe improves performance and fairness over the baseline, regardless of the DRAM-based TRNG of the system. We also evaluate workloads with RNG applications with low required TRNG throughput and show that DR-STRaNGe improves performance of these workloads as well. For more analysis and results, I invite you to read our paper. Now let me conclude. This paper tackles 3 key challenges for using DRAM-based TRNGs in real systems. The RNG interference that significantly slows down concurrent running applications, unfair prioritization of RNG applications that degrades system fairness, and the high latency of DRAM-based TRNGs that degrades the performance of RNG applications. The goal of this work is to design an end-to-end system for DRAM-based TRNGs with low cost and high performance. We propose DR-STRaNGe, an end-to-end system design for DRAM-based TRNGs that reduces the RNG interference, improves fairness, and hides the large TRNG latencies. Based on our evaluations, we show that DR-STRaNGe improves the average performance of non-RNG and RNG applications by 17.9% and 25% respectively. It improves average system fairness by 32% when generating random numbers at a 5 gigabits per second throughput, and it reduces the average energy consumption by 21%. And that concludes my talk. Thank you for your time and attention.